Okay, so in this lecture, before we start the final chapter, we're going to look at anti-differentiation / integration and do a little bit of a revision. Okay, now I'm going to go fairly quick through this lecture. If you want to see a slower treatment from actually a live lecture, you can go onto my YouTube channel and see it there. I think it's called Revision of Antidifferentiation or something like that. Okay, so we'll get cracking. So if we have a positive function, now what that means is, now actually it only has to be positive between 2 points. So for example, this function is positive between 1 and 3. The outputs are between 1 and whatever, 2.25 or something. And then the integral of f, you can almost define it to be the area under the curve. Now, you can make this quite rigorous, but just for today, this is actually how I want you to think about how the integral is defined. If you have a positive function, the integral is the area under the curve. To calculate these things, you use what's called the second fundamental theorem of calculus, which is an expression of the way that differentiation and integration are kind of inverses. So we want to have a look at this. Okay, so to differentiate a function, you find the function f dash, the derivative. Okay, so for example, the derivative of x squared is 2x, and what we're going to use the operator language that we introduced at the start of chapter 2. So d dx of x squared is equal to 2x. Okay, so this is an operator. Okay, takes as an input a function of x squared and outputs another function of x, in this case 2x. So anti-differentiating is doing this in reverse. Now we're going to write this as d dx inverse. Now this is a little bit dodgy, but just for the moment, this is how I want you to think of it. So the inverse operator will bring you from 2x back to x squared. So this anti-differentiation is like running differentiation backwards. So if you have a function x squared and you differentiate it and you get 2x, I'm saying roughly if you anti-differentiate it, you go back to x squared. Now just be wary, this is not quite the whole story. So say d dx, differentiating, and then the inverse, and then we'll talk about the issue in a moment. For the moment, we'll call d dx inverse. So differentiating and anti-differentiating. So this isn't the whole story because 2x has more than one antiderivative. X squared plus 3, if you differentiate it as 2x, x squared minus 4 are two of them. In fact, any function of the form x squared plus c is an antiderivative. So there's kind of heavy maths you need, equivalence classes to make this precise, but what we're going to say is for the purposes of integration, which is finding these, it doesn't matter which one of these you know, whatever the c is, you're going to get the same answer, and that's one sense in which you can say that these functions are equivalent. They're equivalent in the sense of if you integrate them, well, not quite if you integrate them, but if you take this function, whatever antiderivative you want to use, say x squared plus 3 or whatever, you'll get the same answer for the integral of 2x. That's what it means by equivalent. So this c is usually called the constant of integration. I would call it the constant of antidifferentiation, but we'll leave that go. So we think of the antiderivative of 2x for the purposes of integration, where it doesn't matter which one you use, as x squared plus 0. Okay, so I think we're going to see at some stage why we can forget about this c if we're integrating. So what do we got here? So this says that if f is an antiderivative of f, little f, so I think we're talking, oh, this is always a little bit messy because I can never remember. So yeah, I think what we're saying is that the integral from a to b f of x dx, on dx of course, how you calculate this thing is you anti-differentiate f of x. So we're saying that big F is the antiderivative of little f. This is the second fundamental theorem of calculus. And then to, what the hell does this mean? This means substitute in the top limit minus substitute in the bottom limit. So this is how you can calculate these things. This is called the second fundamental theorem of calculus. Another way of writing this would be something like, if you have a derivative here, this is in one sense, what does it mean to say that integration and differentiation are inverses? Well, this is one expression of it. This is a first fundamental theorem as well, but we won't need that. So it says you anti-differentiate, so go from the derivative to the original function. And of course this is the same as above, but what I'll do, I'll just use some color to be a bit more precise. So this is, just refocus. I did an hour of videos yesterday without being focused. Okay, so here you've got the derivative and here's the antiderivative. Okay, in words, to calculate an integral, find an antiderivative, then do substitute top limit minus bottom limit. To calculate the integral of f, we need to antidifferentiate it. So I think what we're saying here, in terms of the diagram we set on the previous page, so if you have f, oh yeah, we're looking to find an antiderivative. So this is our job here. And again, for the moment, I'm going to write this as d dx inverse. It's not terrible maths if you do it properly, but the way we're doing it isn't great. So we're trying to find an antiderivative of little f if you want to integrate little f. And what does it mean to be an antiderivative? It's a function that you differentiate and you get little f. Okay, we said earlier it doesn't matter which antiderivative we use. It can be shown that all antiderivatives of a function differ by a constant. So all are this form. So suppose we used f plus c, and there's funny integrals where kind of get weird things happening. So the antiderivatives look different, but they are equivalent. They differ by a constant, and their integrals will be the same. Well, the integral of the I suppose the derivatives. So we'll just show what happens if you use big F. So suppose you are integrating f of x. So let's say big F is the antiderivative, and we said that little f has loads of antiderivatives. They're all equivalent. So suppose you use one with a plus c instead of a different particular one. Well, there, look what happens here. You get, so substitute top limit minus substitute bottom limit, you end up with f of b plus c minus big F of a plus c. And because, look what you get, c minus c is 0. You end up with the same thing as if, and of course this should be substitute top limit, this should be b. You get the same thing as if you didn't include the constant of integration. So this is why you don't need to include the constant when you're integrating. Okay. Therefore, all in all, we need to be able to anti-differentiate if we want to calculate integrals. Perhaps amongst other reasons, because it's not a perfect inverse, there's a load of antiderivatives. You don't use this notation. Instead, this notation. So this is the notation for antiderivative. You kind of say it anti-differentiate with respect to x. Oh yeah, it's just said there. It's not exactly an operator. It makes a little bit of sense to say this, that anti-differentiate with respect to x is anti-differentiate. It makes a little bit of sense. It's the way to conceptually think about it. Okay. So, if we want to calculate integrals, what we have to be able to do is anti-differentiate. So, by the end of the next week's lectures, we're going to have this general strategy put together. So, the first strategy is to anti-differentiate. You go directly from the tables. We'll talk about what that means. If tables are not available, you do manipulation. And there's special manipulations. Partial fractions you would have seen last semester, and complete the square is a special manipulation we'll see this semester. If it's not in the tables, it's no manipulation work. You try U substitution, and actually we're going to call it W substitution. And then the other new method that we're going to look at is integration by parts. Now this, you can keep on going forever. There's many different techniques of anti-differentiation and even integration, but this is a strategy that we'll end up with. Okay, so basically the first thing to say because antidifferentiation is the inverse of differentiation, we can just run differentiation tables backwards. So the derivative of x cubed is 3x squared, so the antiderivative of 3x squared is x cubed. Derivative sine x cos x, antiderivative cos x is sine x. Derivative log x 1x, and so on and so forth. So any table of derivatives naturally gives you a table of antiderivatives. Just run it backwards. Okay. The three functions, I would say that people see, I'm going to be recommending this strategy, this 4-step strategy, and probably the three functions that people skip over and think they need to do a manipulation or maybe a W substitution are these three functions. These are all in the tables. Antidifferentiation is linear, like partial differentiation and indeed differentiation. So if you have a sum, you can antidifferentiate term by term, fixing constants. You can use a single C, because if you use two C's, you get a C1 plus C2. That's just the sum of constants. That's just some constant. Okay. All right, so we're going to do some examples, and we'll go pretty quickly, as I said. So the first antiderivative we're looking at here is this thing. So what I just said is that if you've got a sum like you do here, you do term by term fixing constants, and we're going to use the tables. Okay, so I1. So first we're going to do 2x cubed, fix the 2 because it's a constant, and then the antiderivative of x cubed is x to the 4, so you add 1 to the power, divide by the new power. So it's going to be x to the 4 divided by 4. Plus, fix the 3. What is the antiderivative then of cos of x? Is sine of x. And finally, fix the minus 2. Now, funnily enough, I don't think this one is in the tables, but you should, if someone asks you what's the exponential function, you should know, oh, it is the unique function that it is its own derivative, therefore it is also a function that it is its own antiderivative, so this leads to x. And the question is, does this get full marks? No, because this is looking for all the antiderivatives. If there's no limits, it's looking for all the antiderivatives, so you need this plus c. Okay. Now, the next one, 4 over x. Now, there's a little manipulation here that 4 over x is 4 times 1 over x. We'll just kind of show why this is the case. If I write down, say, this thing, and if you're looking at that and you say, what is that? There's different things you can say. You can say 2 over 5, which doesn't mean anything. 2 divided by 5, which possibly means something if you can tell me what divides means. But what I actually want people to say here is this is 2/5. 2 by 1/5. And in general, this is how you define a divided by b. It's a by 1 over b. And then what's 1 over b? It's a number we would have seen this when we spoke about matrices. 1 over b is a number that you multiply by b to get 1, and 1 is a number that when you multiply it by any number you get the same thing. Okay, so this means that you can, that 4 over x, where's this coming from here, is 4 times 1 over x. And so if we want to antidifferentiate it, we can fix the constant I2. Sorry, I2 is just the name of this antiderivative. We can fix the constant 4, and we look in the tables, the antiderivative of 1 over x is log of the absolute value of x. Now usually, yeah, look, it's absolute value of x. And again, it's an antiderivative, so it's not an integral. You want all the antiderivatives, you want a plus c. Okay, that's the answer. Next question. So this one, now we should probably start talking about the strategy here. So here the first thing is, you say, is it in the tables? X cubed is in the tables, yes. Cos x is in the tables, yes. E to the x is in the tables, yes. 1 over x is in the tables, yes. What about 1 over 1 plus x squared? So this is one that will catch people out. It is actually in the tables. It's of this form, 1 over a squared plus x squared, where the a squared is 1. So this is, if I just write down here, this 1 here is like a 1 squared. Now you can say, oh, 1 is a square number, that's great. What about if I had, for argument's sake, 1 over 7 plus x squared, if I wanted to antidifferentiate that? Now, any positive number can be written as a square, because what you can do is you can say that it is the square root squared. So anything of this form is of this form. Anything of 1 over a constant plus x squared, as long as that constant is positive, you can write it as in this form. So we'll anti-differentiate directly. I3 is equal to, so 1 over a, now here the a is 1, inverse tan x over a, and as we said, the x is 1. Now, really we probably should tidy this up, because 1 over 1 is so simple, it's just equal to 1. 1 by anything is itself. X divided by 1 is just x, so you get tan inverse of x. And of course you want to do, because it's just anti-differentiation, plus a c. Right. Now if the thing, so they're the easy ones as such. If the thing that you're trying to anti-differentiate is not quite in, if it's not maybe a sum of terms, you're in a bit of trouble, because there's no product rule here. Well, integration by parts would be like a product rule, but these are all a sum. Like if you had x cubed by cos x, you couldn't send them back individually. So for example, let us write, say, x cubed, and this is probably the biggest mistake people would make when they start this. You can't send this back individually. This is not equal to, sorry, not send it back. You can't anti-differentiate individually. This is not x to the 4 over 4 times sine of x. It's just simply not true, because they're multiplied together. You can only do it term by term if they're a sum multiplied by constants. You might say, oh, is there a product rule? Well, not straight away. So if you've got x cubed by cos x, as it happens, this is probably a little tricky little thing to handle. It would take a while to do it. You would technically be able to do it after we see this new technique of integration by parts. Anyway, so the story is, what we're looking at here is, if it's not this easy, can we maybe rewrite this thing? That's called a manipulation. Now, x cubed times cos x, you can't do anything with it in terms of manipulation, so you'd have to try a substitution, which you'd find doesn't work. You'd have to go at this with parts. Okay, so let's look at the different manipulations we're talking about. So the first one is negative power. So if you've divided by a power of x, if you know your way around indices, if you know your basic maths, you know that multiplying x's together is positive power and dividing x's is a negative power. So 1 over x cubed is x to the minus 3. So what you can say is that if you have, say, 1 over x to the n and you want to anti-differentiate it, you rewrite it as x to the minus n. Now it's important here that you understand this is not anti-differentiating. Equals doesn't mean this goes to this. These equals means these are the same. So if you want to anti-differentiate this, instead you can anti-differentiate this, and then you can use the table antiderivative, which says that if you have any power of x, now I'm gonna use m, which isn't quite what the tables use. I think this works for basically m is any number except for -1. We'll see about that. Okay, actually we may at this point go back to the log of x example. Probably be a good idea. So once we do this, we'll do it just here. The question would be, oh, what about the antiderivative of 1 over x dx? How about I don't look in the tables and see that it is antiderivative is log of absolute value of x. What if I do the manipulation? What if I rewrite this as x to the minus 1 dx? And this power rule that I'm about to write down says if you're anti-differentiating a power of x, you add 1 to the power, divide by the new power. And I'm saying this is the case for any power. Now it gets a little bit tricky if the power isn't a fraction, but we won't worry too much about that. Okay, there's an interesting comment here about how do you know, for example, that the antiderivative, say x to the 2/3 is x to the 2/3 plus 1 over 2/3 plus 1. Well, you get it from the differentiation, and the question is, how do you know that the derivative, say, of x to the 5/3 is 5/3 x to the 2/3? How do you know that? It's actually implicit differentiation that shows that implicit differentiation that we did in the previous chapter. Right, that's a bit of a sidetrack. Well, anyway, here we're saying that this is basically holds most of the time. This is your only problem. So if you do add 1 to the power here, you get x to the 0 divided by 0. And we should know at this stage division by 0 is a problem. This is undefined. And what is the solution? Well, the solution is that the antiderivative of 1 over x is log of x. Okay, so this is true for as long as the power is not -1. Okay, so for example, if you want to antidifferentiate, say 1 over x cubed, for example, what you do is you rewrite 1 over x cubed as x to the -3. These things are equal, so their antiderivatives are equal. And now what we do is use this power rule. Add 1 to the power. Now you have to be careful, just slow down. -3 plus 1 is -2. Divided by -2 and then plus c. We won't worry too much about simplifying this at this time. Okay. Right, so what about these kind of funny things with roots? So again, if you know your way around surds, first of all, you would know that the mth root is the power of 1 over m, so that this object here is equal to x to the n all to the power of 1 over m. And then you would know that repeated powers, you multiply the powers, x to the n by 1 over m, and you would know from what I did in the previous page that m by 1 over m is equal to x power of n over m. And this power rule also works for fractions. So for example, if you wanted to antidifferentiate, let's say the square root of x cubed. Now you don't take 2 steps, you do it in 1. So the square root is the second root. Okay, so basically if you look at this, the power is here and the root is divided by. Okay, so this is the same as, so it's x cubed square root, like that. And now we can do our manipulations. So we get add 1 to the power, so 3 over 2 add 1 carefully is 5 over 2. You could use 2.5, but it's a little nasty, divided by 5 over 2. Now there's one manipulation I probably recommend here, and it's about, yeah, look, there's different ways of arguing this, but you should know that dividing by a fraction is multiplying by the inverse, and the inverse of a fraction is the flip, or the reciprocal. So dividing by 5 over 2 is the same as multiplying by 2 over 5. And then of course we get a plus c. Other manipulations include multiplying out. So for example, see this, it's multiplied together, you should multiply it out. Because remember, you're good with sums. If you root x by 1 is root x by root x is x is x to the half, and then you can use the power rule and you're done. Another example, multiply this thing out carefully. Write it as a sum, and if it's a sum, you can antidifferentiate term by term. So in general, you're not good with things multiplied together, but if you can write them as a sum, if you can multiply them out, you'll be able to antidifferentiate. Now, this one is probably a bit harder than what we'll... Oh, well, the first one is okay. So if you've got something divided by something, you might be able to divide in. So this is using the fact that basically, say if you've got 2 elevenths plus 3 elevenths, this is 5 elevenths, which is 2 plus 3 elevenths. And this is just saying that you can run this backwards. You can split up the sum like this, and then you have to use a few different things. You need to know that, so your algebra will get tested in a question like this. Square root of x is x to the half, and division of like powers, you subtract the powers. So this would be 2 minus a half, and then this is 1 over x to the half, and dividing by a power is a negative power, so this would be x to the minus half, and off you go. The other example is harder, but something like this you actually can handle. You can do polynomial long division. Now that won't be examined, so I won't be too worried about it. The other thing we probably won't see is trigonometric manipulations. So there's loads of things. So for example, if you're asked to antidifferentiate cos squared, you could write it as a half 1 plus cos 2a, and these are in the tables. Now we'll worry about cos 2x a little bit later on. Another example might be something like this. This looks very, 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 very nasty, because remember we said we don't have a product rule. So if you know about trigonometry, you know that sec of x is 1 over cos of x, and so you have cos of x divided by cos x is 1, so this is actually just the antiderivative of sine of x. So this very complicated thing is actually quite easy. So these are manipulations. There's loads of trigonometric manipulations, probably harder than we will look. More advanced things, partial fractions, which are going to be very important if you go to level 7, but are not so important here, even though you would have done them last semester. So for example, 1 over x cubed minus 1. Partial fractions is taking a complicated thing and writing it as a sum of simple things, and you can anti-differentiate these using substitutions. We're going to see a more complicated manipulation, which is called completing the square. We are going to see that in this module. So you basically turn quadratics into sum or differences of squares. Okay, so I think that is enough on the manipulation. So where are we at the moment? We're just saying if you need to do an integral, or indeed an antiderivative, your first two things to try, look in the tables. Is it in the tables? If it's not in the tables, do a manipulation first.